Okay, we will start with the today's class. In the previous class, we have discussed about designing of the counter, that is synchronous counter for a particular count sequence, that is the counter counting in the up direction or the down direction. And now we have seen how it can be designed using D as well as T flip-flop. In fact, same can be designed also using JK flip-flop and SR flip-flop. So in today's class, we'll see how we can design a up-down counter. Then we'll see how we can design a random counter for a given count sequence using again D, T, SR and JK flip-flop. So first we'll start with designing of the up-down counter, that is binary up-down counter. So here I have shown a state diagram for a 3-bit binary up-down counter. So when I say 3-bit, it needs 3 flip-flops, right? And the count sequence what we'll be getting is of 3 bits. And when it is up-down counter, we should have one more control signal. Like depending on that control signal, either the counter should count in the up direction or in the down direction. So we can take one control signal like up/down bar. What is the meaning of this up/down bar? Can anybody tell me? Because here I have used one control signal called up/down bar. So what it means, this particular signal you can see here, right? So it indicates that when this signal is 1, it will count in up direction, right? And when the signal is 0, it will count in the down direction. That's why it is written as up/down bar. That means for up it should be 1 and for down it should be 0. So this is the control signal we are using, up/down bar. Any control signal you can name, maybe I'll name it as yum. So if yum is 0, it will be counting in down direction. And if yum is 1, it will count in the up direction. So that is the additional thing that you need in this up down counter apart from the 3 flip-flops. All right. So depending on this up down signal, it will be counting in the up direction or in the down direction. So you can see from this state diagram here, this is the first state I have shown 0 0 0. So if the counter is in this state and if the up/down bar signal is 1, it will go to 1 state. Similarly, if it is in 0th state and if this up/down bar signal is 0, instead of going to 1, it will go to 7. That means it will count in the down direction. So here you can see this is up, this is down, and that is differentiated using this up/down bar signal. If that signal is 1, it will count in the up direction, and if the signal is 0, it will count in the down direction. Similarly, if the counter is in this direction, in this state, if up is 1, it will go to 2, and if up is 0, it will go back to 0. So from 1, either it will be going to 2 or it will be coming to 0. That again depends on this up/down bar signal. Similarly, the same thing will continue if it is in 2 state. If the state is 2, it will go to 3 if up/down bar is 1, and it will go to 2 if it is 0. Similarly, from 3, it can go to 4 or it can come back to 2, depending on the up/down bar signal. And if it is in 4, it may go to 5 or it may come back to 3. So if it is in 5, it may go to 6 or it can come back to 5. If it is 6, it will go to 7 or it will come back to 5. And if it is 7, it may go back to 0 if up/down bar is 1, or it may come back to 6. So this is called as the state diagram or the state transition diagram of the up-down counter. Right. So once you have the state diagram, very easily you can construct the truth table. Right. So only thing in the truth table, now you have to take one additional signal, and then you have to take the present states denoted by maybe C, B, A, or A, B, C, or QA, QA, QB, QC. You can denote the 3 states by any signal. So we'll denote the 3 states by A, B, and C. In addition to that, we'll take one control signal yum. So how we should write the truth table for this? Can anybody try? first you have to write the control signal M, then you have to write the present state. Present state you will be denoting it by what? C, B, A, right? Then you have to write the next state, and next state is denoted by what? C plus, B plus, and A plus. Right. So can you construct this truth table? Just write the present state and next state and the control signal M. I want to see how many of you can write that. Can you do it? Yes. Will you able to write the truth table? Actual truth table, when you are writing the designing the counter, I have told first you have to write the present state, then you have to write the next state, then from the present state and next state you have to derive the flip-flop inputs using the excitation table, right? And then those flip-flop inputs what you are getting, you have to get the Boolean equation using the K-map. That is the normal process that you will be using in designing the counter. Now since here we have up and down signal, so you have to add that control signal extra as the input along with the present state. Here I have told the present state should be denoted by CBA, and then you have to get what should be the next state, that is C plus, B plus, A plus, and then we have to derive what are the flip-flop inputs. And to be to make the design simple, first we'll use the D flip-flop, because you know that the advantage of D flip-flop is that whatever the next state you are having, that itself is the flip-flop input. So you need not bother about the excitation table also. So directly you can get the flip-flop inputs, which are nothing but the next states of the counter. And by using those flip-flop inputs, you can get the expression for DA, DB, DC, and you can draw the final logic diagram of this up-down counter. So I want first you should write the control signal M, which can be either 0 or 1. If it is 0, the counter should count in down direction, and if it is 1, the counter should count in up direction. So you have to write the present states and what should be the next state. For all of these present state you have to write depending on the control signal, and then finally you can write the flip-flop inputs. And again I am repeating, when you use a D flip-flop, flip-flop inputs will be nothing but the next states of the counter. And then you have to use the K-map. In this case, you have to use 4 variable K-map. Why? Because 3 for the states of the counter and 1 the additional input, that is up/down bar signal. So totally 4 inputs will be there. So you have to use 4 variable K-map for DA, DB, DC, and you have to get the expression for DA, DB, DC, and then you can draw the logic diagram. So can anybody has written the present state and next state for this up-down counter? Again I am repeating, if you understood this designing of the counter, very easily whatever may be the count sequence they get, whatever may be the flip-flop that they ask you to use, very easily you can design the counter. In fact, as I said, you have to do it in your laboratory also. So once you know the designing, you can very easily you can play with the designing of the counters using any of the flip-flop. Yes, anybody has done it? At least you have written the present state and next state. If you have a state diagram or the state transition diagram, writing the present state and next state is very easy. And once you write the present state and next state, very easily you can derive the flip-flop inputs using the excitation table. And in that, when you use a D flip-flop, even you don't use the excitation table, directly you can write the flip-flop inputs as the next state of the counter. Yes, anybody has done? Yes? Yes, Sahana? Can you tell me what are the present state and next state for this? Yes, Sahana Joshi. Are you there?
Yes, sir. Yes, sir.
Yeah, can you tell me what should be the present state and next state depending on the control signal? Because that is a very important part in designing the counters. Right? Yes?
So control signal, sir, what is the control signal?
Control signal you can denote by anything. Up/down bar that is the control signal actually. That will decide whether the counter is counting in up direction or down direction. I told you can denote it by say M, mode. Right? If you take it as a M, that
Yes.
indicates the mode of the counter, whether it is up counter or down counter. So if M is 0, it should count in down direction, and if M is 1, it should count in up direction.
Yes, sir. So if it is 1, it will count, I guess, 001. And
So
then,
you have to write present state, next state. So
oh,
you have to make one column for the present state, one column for the next state. And then
present.
initially you make one more column for that control signal M.
Yes, sir. So present state will be 000, right, sir? Beginning.
Okay.
And then if it will be 1, the signal, then it will go to the next one, like count upwards. It will be 001.
001. Okay.
And if it will be 0 signal,
So
then it will
what you do is first assume that M is 0 and write all the present state and next state. Right.
Yes.
Then you assume M equal to 1 and write all the present state and the next state, so that there will not be any confusion. Instead of writing both, like when M is 0, M is 1 simultaneously, you take M equal to 0 first.
Yes,
and write down all the present state and next state. Then take M equal to 1, write down all the present state and next state.
Yes.
So assume initially M equal to 0 now, and write down the present states.
1 1 1 it will count, right? So
yeah, first 0 0 0. Right? It is 0 0 0. Next state will be 1 1 1.
So
right? Then if the present state is 1 1 1,
next will be 1 1
1 0. Like that. If present state is 1 1 0,
next one will be 1 0 1. It will count down.
Yes, like that you have to write. And this is what is the present state and next state table. You can see here everything I have given. Just all of you try to understand what is happening there. This is a very simple example and very important example actually. As I said, I have taken, this is M. So initially I have taken M equal to what? 0. So when M is 0 and if your present state is 0 0 0, next state is what? 1 1 1. Say if the present state is 1, next state will be 0 0 0, down counter. If the present state is 1, next state is 0 0 1. If the present state is 0 1 1, next state is 0 1 0. So you write what? M is equal to 0 and write all 0 to 7 here. And based on that, you write what is the next state. Similarly, when M is 1, again we'll have 8 states, that is 0 0 0 till 1 1 1. So what is the difference here? You can see when M is 0, present state is 0 0 0, next state is what? 1 1 1. But when M is 1 and if the present state is 0 0 0, what is the next state? What is the next state, Sana? It is
0 0 1.
So, right? So if 0 and if the present state is 0 0 0, next state is 1 1 1. So what you have to do is totally 4 inputs you are having. So write those 4 inputs means 16 input combination right from 0 0 0 0 till 1 1 1 1. And then you check what is the present state, what should be the next state. Similarly, present state, next state. So here in the first half, it is down counter. In the next half, it is up counter. So once you write the present state and the next state, then depending on the present state value and the next state value and using the excitation table of the D flip-flop. This is the excitation table of the D flip-flop. You can write what are the flip-flop inputs. Now you can see here, if the present state is 0, next state is 1. What should be the D input? 1. DC input, you have written it as 1. Similarly, 0 0 means it should be 0. 0 0 again 0. So in short, whatever is here, the same thing you should write it here. Right? Similarly, for B plus C plus, if you write, you will get the flip-flop input. So what should be the DC input? We got here 1 0 0 0 0 1 1 1, then 3 zeros, then 4 ones, and again 0. Similarly, we'll get DB input, that is D input of the flip-flop B, and this is the D input of the flip-flop A. So from this truth table, or you can call it as a synthesis table or the transition table, we got the flip-flop inputs DA, DB, and DC. What is the next important step now? I hope all of you clear with this till this point. Till this point, all of you understood? Just I have taken one additional signal M here to indicate count up or count down. And based on what is the present count, we have written the next count. And based on this next state, we have written what should be the flip-flop inputs, that is DC, DB, DA. Now what is the next step here? Yes, Omkar, what we should do next? Yes, what we need to do next? In the previous class, I explained so many examples. That means you people have not understood it. Have you understood it or not?
Sir, K-map.
Yeah,
Sir,
K-map.
K-map
How
program
many
from.
K-map and how many variable K-map we have to use? How many flip-flop inputs are there? Those many K-maps you have to solve. So how many flip-flop inputs you are having?
3.
Because you have used, if you use D and T flip-flop, you will get only 3. That is equal to number of flip-flops. But if you use JK and SR, you will get the number of inputs double than the actual number of flip-flops, because those two flip-flops, they have two input, either SR or JK. So here we are using D flip-flop, means we have only 3 inputs, that is DC, DB, DA. Now how many variable K-map we have to use? So far, we used to have only this flip-flop present state, right? We used to have this, and based on that, we used to derive the equation for the flip-flop inputs. Now, how many variable K-map we have to use? You have to include this yum also here. So, total number of inputs will be how many now? How many? Total number of inputs are how many now? There are 3 inputs for the 3 flip-flops, but in addition to that, we have a control signal M. So total number of inputs are how many? 4.
4.
So you have to use 4 variable K-map. So you need to draw a 4 variable K-map, and what all inputs you have to take here is M, then C, then B and A. MCBA, sorry, MCBA it should be, right? Here it has become A actually. This should be B, right? And this should be A. You should take it in that particular order only. MCBA. This is not A. This is B. This is A. Is that clear? So how many K-maps you have to solve? 3 K-maps of how many variables? 4 variables. 4 variables. 3 K-maps you have to solve like this. It is given already, you can see MCBA, and simplification is already given. You have to try it, just don't copy this. Anyhow, you know how to solve the K-maps, right? Maybe this is what you are getting. You can think how you can do the grouping here. Maybe I can do this one as a grouping. This is one group. This is another group. Right, then this cannot be combined with anything. So this is one, this is one, and write down what you get. Right, it is not that you may get this. It depends how you are doing the grouping. In fact, that is the disadvantage of the K-map. There is no fixed or standard procedure as such for the simplification. So you can do these groupings and you can write, and then they have simplified it further and written in terms of XOR operation. Similarly, here we can do the grouping. I can form one pair, here I can form another pair, here I can form another pair, and here I can form another pair. I can't form the bigger groups, right? And lastly, here what I can do in the third K-map, how we should do the grouping? How we can do the grouping in the third K-map? We can combine
Form octet to 1 octet.
these 4 and these 4. If you combine, actually you will get this is the common, and that's what is written DA equal to A bar. Right? This is simple actually. Getting that table is important. Once you get this table and if you write the correct flip-flop inputs, then you have to take these for each of the K-maps, simplify, you will get these equations like this: DC, DB, DA, and last step is using these equations and using the 3 flip-flops, you have to draw the diagram. So here I have shown 3 flip-flops. This is flip-flop C, flip-flop B, and flip-flop A, right? So clock is given directly. Actually, it is shown separately, but you can show it like this. This is the clock. A common clock can be connected, and then you can take the outputs also here: C, B, and A. This is A output. This is B output. This is C output, right? Then you can see here DA equal to A bar. So this has to be connected here. Actually, that connection is not shown. You have to show the connection. Take A bar and give as an input to D. Then what is DB? As per that equation, XOR operation of this all, M and A, actually you should show one control signal. Like clock is one signal you have shown. Like that, you have to show one more external signal, M. And wherever M is required, you need to connect M or M bar, whatever you need, you have to connect that, because all those connections are not shown here to be for simplicity, but you need to show all these connections. And this is what is the designing of the up-down counter. I hope all of you understood this. Any doubts here? Again, I am repeating. I started with this state diagram. This state diagram we have converted to this synthesis table or the transition table or the truth table of the counter. And from this truth table, we have used this flip-flop inputs, and we have got the equation for this flip-flop input DC, DB, DA using 3-4 variable K-maps, right? And when we use this 3-4 variable K-map, we have got this DC, DB, DA. Now using these three equations, we have drawn, this is the logic diagram for the 3-bit binary up-down counter, which counts in up direction when M equal to 1, and it counts in down direction when M equal to 0. So that is the designing of a 3-bit binary up-down counter. I hope it is clear. All of you understood it? If you have any doubts, any difficulties, you can ask before I proceed further. Right? So just by listening to me, you will not understand. Actually, you have to sit, you have to work out with this, you have to solve this, then only you will be confident. And I am sure once you solve it, you will never forget it. Right? So I request all of you, after the class, whenever you get a time, just try to redo this, whatever I explained. You take a pen and paper and try to design this. If you design one counter, I am sure you will get the confidence, and whatever may be the counter design they ask, very easily you will do it. Again, I am repeating here, the important steps in designing the counter is, first you should know the state diagram, or at least you should know the state transition, how the counter is changing its state from which state to what state. If you know that, easily you can write the present state and next state of the counter. And once you write the present state and next state, then using the flip-flop excitation table, you have to write what are the flip-flop inputs depending on the chosen flip-flop. What flip-flop you have chosen to design, for that flip-flop, whatever is the excitation table, you have to make use of that excitation table, and you can derive the flip-flop inputs. And once you derive the flip-flop inputs, then you can use the K-map and you can get the expressions for those flip-flop inputs. And then using those expressions, just you have to do the interconnection of the different inputs and outputs, and you can complete the logic diagram for that particular counter. And that is how we can design the binary counter. Whether it is only up counter or down counter or up down counter, the design remains same. The only difference in the up down counter is, as I said, here you need to use one additional control signal or the mode signal like this M. Otherwise, you have seen in the previous class, we have not used any control signal because that was only up counter or down counter. But when you want to include both in single, then definitely you should have the mode signal, which indicates whether the counter should count in up direction or the down direction. I hope it is clear. Any doubts? Yes? I need your feedback, whether you understood this or not. If you have not understood anything, you can ask. I will explain that portion once again. But just blindly don't say that, yes, I have understood. All of you understood? They say at least yes or no. That's what many times when I ask, there will not be any response from you people. Right? I think only one response I got in the chat box. Right, 1 or 2. Right? Others, I don't know whether you understood it or not. Yes, Rehana says it's understood. Good. Shall we move forward if you understood? Because these are the basic designing of the counter. Now I will be moving forward, wherein we'll be seeing the designing of the other counter. And this is the timing diagram given here based on the M/N M signal. If it is 1, you can see it is counting in up direction, and if it is 0, it will count in the down direction. This is a timing diagram for this up down counter, right? All of you understood so far? Whatever the examples we have taken here, they were the natural count sequences, either say 0 to 2 to the power n minus 1 or 2 to the power n minus 1 to 0. That means they were counting in natural count sequence from 0 to the higher value or higher value to 0, and that's how we got up counter or down counter. And in the last example, we have clubbed both, and we have seen how up down counter works. Now they may ask you to design a counter not for the natural count sequence. They may require a counter which will count in different count sequence. Maybe first it should give 0 output, then from 0 it should go to 4, then 7, then 2, 5, 8, like 6, like that. Different count sequences it may get asked to design, and such counters are called as the random counters, right? Maybe here I have shown 3 different examples. Like it is having in 110, that is 6, it remains in 6, or 7, or from 6 to 7 and 7 to 6 only. Such counters, if you want to design, they are called as the random counters. So how we can do designing of such random counters or irregular counters? So an irregular counter is the one in which it does not follow any regular or natural count sequence, but it will have n different distinct states, and thus we can call it as a mod n counter. Again, it will have different states, but they are not the regular binary sequence or the natural count sequence. Such counters are called as irregular counter or the random counter. So now we have to see how we can design a random counter. So I have given you one example here. Can anybody tell me what is this counter doing? What this particular counter is doing? Yes, Namita? They ask you to design this counter using T flip-flop, and already state diagram is given to you. So what you can understand from this state diagram, what is this counter is? It is, yes, Namita?
Yes, sir.
What is this counter doing? Because they ask you to design this synchronous counter using T flip-flop. Before we proceed with the designing of this counter, you should know what this counter is doing. And that easily you can explain by looking at the state diagram or the transition graph or the transition diagram. What it is doing? In fact, it is having how many different count sequences? Yes? It is having how many different count sequences? 5. But it is not counting from 0 to 4. When I say 5 count sequences, normally the counter will count from 0 to 4 or 4 to 0. But it is not counting from 0 to 4 or 4 to 0. It is counting in different count sequence. Hence it is called as a random counter or irregular counter. What is the first state of this counter? Yes? You can start from any one point. We'll take the first state as what?
0, 0, 0.
0, 0, 0. From 0, 0, 0, it is going to what? 1, 0, 0. That is from 0, 0, 0, it will go to 1, 0, 0. And then from 1, 0, 0, it is going to what? 1, 1, 1. Then 0, 1, 0, 1. That means first it
1,
is
1, 1.
0, then it is 4, 7, 2, then 3. So it should count continuously in this count sequence. From 0, it should go to 4. Then from 4, it should go to 7. From 7, it should go to 2. From 2, it should go to 3. And from 3, again, it should go to 0. Right? This is what the random counter you have to design. So how many bit counter it is again?
3 bit.
3-bit counter. So I can denote those 3 bits by what? C, B, and A. Right. What is the first state we have here? What is the first state?
0, 0, 0.
0, 0, 0. And what should be the next state for this? If you write C plus B
1, 0,
plus
0.
A plus. If C, B, A is 0, 0, 0, what should be C plus B plus A plus?
1 0
Yes,
0.
1, 0, 0. Yes, good. Similarly, if the present state is 1, 0, 0, what should be the next state?
1 1 1.
1 1 1.
1, 1, 1. Then if the present state is 1, 1, 1, what should be the next state?
0 1 0.
0, 1, 0. Like that, you can write what is the present state, what is the next state, and once you write the present state and next state, very easily you can write what should be the flip-flop inputs. And once you write what should be the flip-flop inputs, then you can use the K-map and you can get the equations for the flip-flop inputs and you can draw the logic diagram. I hope it is clear, the process, what you need to do. So that is what is shown here, right? So one important thing you should remember here is, in fact, I told here, whenever it is 0, 0, 0, it should go to 1, 0, 0. If it is 1, 0, 0, it should go to 1, 1, 1, right? But when you are designing the random counter, what you do is, present state you write in the sequence. First you write 0, 0, 0, right? Then you write 0, 0, 1. Then you write 0, 1, 0. Then you write 0, 1, 1, then 1, 0, 0 till 1, 1, 1. But then you may ask, here I have written 8 states, but we are using only 5. What about the remaining 3? So remaining 3 should be considered as what? Don't care. Is that clear? Because you can see here, I am not using this particular state. 1, 0, 0 is not there. So what should be the next state for this 1, 0, 0? What you should write? Yes, you should write it as don't care. So that your writing of K-map becomes easy and very easily you can design the counter. Okay, so you can see here what I have done is present output or the present state you can write. I have written it in sequence 0, right? 1, 2, 3, 4, 5, 6, and 7. If the present state is 0, 0, 0, what should be the next state from this diagram? Yes? Omkar, you can tell me?
1
1, 0, 0. If the present state is 0, 0, 1, what should be the next state? So you have to check whether this state is there here or not. Is 0, 0, 1 is here? Is this state
No, sir.
0, 0, 1 is present in this given state diagram? Is it present?
No, sir.
Then that should be considered as what? Don't care.
Don't care.
That should be considered as don't care, and straight away you should write here also don't care, because that particular state is not there. Then you may ask, if it is not there, why we have to write? The advantage of writing this state is you are writing all the present state in a sequence from 0 to 7, so that entering into the K-map becomes simple. Otherwise, you will do the mistake while entering into the K-map. If you write it in sequence, what you do is, whatever you are getting here, no, 1, x, 0, 0, you can write it in sequence. That is 0, 1, 2, 3, 4, 5, 6, 7. In that particular cell in the K-map, you can enter. That's why this additional state is written. Similarly, if it is 0, 1, 0, what is the next state? 0, 1, 0, next state is what? 0, 1, 1. For 0, 1, 1, you should check whether it is, 0, 1, 1 is there. Next state is 0, 0, 0. 1, 0, 0, 1, 0, 0 is here. Next state is 1, 1, 1. 1, 0, 1 is not there. So write XXX. 1, 1, 0 is also not there. So write XXX. 1, 1 is there. And next state for 1, 1 is what? 0, 1, 0. So 0, 1, 0. So you have written present state and next state. Now you have to write the flip-flop input. Which flip-flop they ask us to use? T flip-flop. So you should know the transition excitation table for the T flip-flop. If it is 0, 0, T is 0. Whenever there is a change from 0 to 1 or from 1 to 0, that time T is 1. Otherwise, T is 0. This you have to remember, and you have to complete this flip-flop table. So how we should write this flip-flop inputs? First, you should check this 0, 1. So what you should write? Yes, Namita? If C is 0, C plus is 1, then what should be TC?
1.
Why? Why it should be 1? I have written 1 here. Why it should be 1? Because
By excitation.
By excitation table. Yes,
Excitation
very
table.
good. That is when there is a change from 0 to 1, from 1 to 0, t should be 1. Otherwise, t should be 0. So first we have written. Second, you need not write because there is a don't care. Go to third. 0, 0. So what you should write again, Namita? 0,
0.
0 is 0. Good. Very good. So like this, 0, 0. What you should write again? 0.
0.
Then 1, 1.
That is 0.
That is also 0. When x is there, don't
It is
bother.
don't care.
Then 1, 0 is what?
1, 0 is 1.
1. So this, by comparing C and C plus, you will get TC. Similarly, how will you get TB now? By comparing B and
Comparing B and TB.
E plus. And how do you get TA? By comparing A and A plus. So I got now equations flip-flop inputs TC, TB, TA. What is the next step now? You have to write one K-map for TC, one K-map for TB, one K-map for TA. How many variable K-map you have to use now? So you should check
3.
how many inputs
3
are 3 variable only, because here there is no control signal as such. So three variable K-maps you have to solve. You can use CBA and one for TC, one for TB, one for TA, and you will get TC is equal to this. This you have to solve. Actually, you know how to solve the K-map. I need not explain that again. So TC, TB, and TA we got. What is the last step? Last, what we should do? Yes? Once you get the flip-flop inputs TC, TB, TA, you have to go for the last step in designing the counter. And what is the last step?
Logic diagram.
Yes, logic diagram. This is the logic diagram. You can see that. Right? I have shown the clock, flip-flop A, flip-flop B, flip-flop C. This is flip-flop A, flip-flop B, flip-flop C. Common clock should be given. Negative edge triggered clock we have shown. Then you have to write TA. What is TA we have got here? TA is C plus B. So how I should get that TA? C plus B means I have to use OR gate. So just I have written here C and B. But actually what you have to do here is this B should be taken and connected here, and this C should be taken and connected here. Okay? B or C should be given. Similarly, you need C. So already C you are having here. This itself you can give here, right? Then this B bar you should take and give. Then C bar you can take and connect here, and then A. Okay, just randomly I have connected. You should do it proper connection. Similarly, C and B, again take C, connect here, take this B, give here, then similarly C bar and B bar you take and give here. That completes. Just for the simplicity, here I have not shown these connections, but compulsory in the exam you need to show all these connections. You should not write only that C, B, C bar, B bar and so on. I hope this design is clear now at least. If you understood this, I can say that you understood counter design. You can design counter for any count sequence. So if you have any doubts, you can ask. Right, this is the timing diagram shown. Similarly, like the same counter what we have designed. So far in designing of the counter, we have used only D or T flip-flops because those are the simplest thing of using, because they have only single input. Now we will see how we can do the designing of this counter using SR and JK flip-flop. Again, don't go panic. Everything remains same. Only thing we get one additional input for each flip-flop. That means instead of using 3 K-maps in this case, next you have to use 6 K-maps. So a little bit work involved will be more, but the procedure remains same, and very easily you can design the counter for any count sequence in using any of the flip-flop. So again the same example. Here they are asked to design what? Using, this is very important example from your examination point of view. You may get it in your third CI also, right? Either designing of this random counter using SR or JK. Like how we should do this designing using SR and JK flip-flop. Yes. What is the first step in this again? Can anybody tell me what should be the first step? Yes, Rehana. How do you start designing this?
Yes, sir.
Yes, how we should design this? From where we should start? Previous example, this you understood, no? Same again, you have to write present state, next state, flip-flop inputs. Now, since you are going to use SR flip-flop inputs will be different. 2 flip-flop inputs you will get, like SA, RA, SB, RB, SC, RC. There you have written TA, TP, TC. Like that, here you are going to get 6. So, but the procedure remains same. What is the first step? You have to write the present state, that is CBA. These are the present state, CBA. Then these are the next state, C plus B plus A plus. But now you can see how many flip-flop inputs we have shown now here. How many flip-flop inputs are there? 6. So far we used only 3, but here we will get 6 now, because each flip-flop will have 2. Flip-flop C will have these 2 inputs, flip-flop B will have these 2 inputs, and flip-flop A will have these 2 inputs. So how do you get this? Using this excitation table now. You should know the excitation table of SR flip-flop. When there is 0, 0, S and R values should be 0x. 0, 1, S should be 1, R should be 0. 1, 0, S should be 0, R should be 1. And when both are 1, 1, S should be X and 0. Using that, you have to fill this. Like you can see here, 0, 1 means what I should write? 1, 0. Then here it is 0, X means X. Anyhow, this state directly you can write X, 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 X for all. Here also you should write X, 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 X. This also you should write X, X, because those are not the valid states. Right? Next you can check again. 0, 0 means 0x. 0, 0 means 0x. 1, 1 means x0. Now 1 and 0. What is 1 and 0? You can see here from this 1 and 0, what is this? 0, 1. So you have to write 0, 1. From 1 and 0, it should be 0, 1. Like that. For this B, B plus, A plus, you have to write SB, RB, SA, RA. So now how many K-maps you have to use? How many K-maps you have to use? You have to use 6 K-map of 3 variables. So 1 K-map you have to use for SC, 1 for RC, 1 for SB, 1 for RB, 1 for SA, 1 for RA. And that's what is shown here, 6 different K-maps for RC, SC, RB, SB, RA, SA. What all you should enter here? I'll take this example RC1. So what we have in the RC? You can see 0xxx, 0xx1. All are x, only 0th, 5th, and 7th. It is 001. You can see here 0th, right? Which is that? Actually, 0th is 00. These two are 00. They are not shown. This is 1 and x, right? This is 001x. So how you will do the grouping? Obviously, I can form a quad of this. So we'll get what is this A. So RC is equal to A. Similarly, SC equal to B bar. Then RB, SB, RA, SA. You can get from these schema. Here what the blank indicates, it is 0. You have to enter 0 there. Here also you need to enter 0, 0, 0, 0, 0, 0, 0, 0. Right? And finally, you can draw the logic diagram. Again, you can show here, I have shown the common clock, and then whatever the equations, just I have written RA equal to A. But I have told, actually what you need to do is, this A you need to take and connect here. Then this B bar should be taken and connected here. Like that, we need C. So this C should be taken and connected here. Then this A, what you have taken, should be connected here. And similarly, these also should be connected from the respective position. And this is the designing of the same random counter using SR flip-flop. All of you understood this? Yes or no? If you understood this, I want you people to design the same counter using JK flip-flop. Right? That you have to do it as a homework. And in the next class, we'll see that one more example. Right? So if you have any difficulties, any doubts in this, Before we stop for the day, you can ask me.